Well, let's continue our discussion of Chapter 2, The Lore of Running, by Tim Noakes. And we'll continue talking about VO2 max. So we know VO2 max is the maximum rate of oxygen consumption. Well, what does VO2 max really measure? What is its value to athletes? And really importantly, and an interesting question is, why do people stop exercising at the end of a graded exercise test or at the end of a marathon or Ironman? Why do people collapse? And that's a really neat question to try to answer. All right, so let's look at this a little bit. So Noakes goes through the history of VO2 max, or measuring VO2 max, and he presents these two studies in Chapter 2. And this is a good section to read through to get a little bit of history on measuring VO2 max. So Hill and Lupton did some of the original work on VO2 max, and the result of their work, they have these data. This is rate of oxygen consumption on the y-axis in liters per minute, and that's okay, that's a rate. We just don't, in these data, they're just not normalized to body mass. And then down here is running speed. And as we know, running speed increases during a graded exercise test. So what this model proposed was that there was a universal maximum rate that oxygen could be used. And that universal number was 4 liters per minute. That means everybody, this was the hypothesis, every person had a universal VO2 max of 4 liters per minute, or humans did. And that occurred at a speed of 13 kilometers per hour. And if you wanted to run faster than 13 kilometers per hour, say 15 kilometers per hour, you would convert chemical energy to mechanical energy using the aerobic pathway. And you would also need to generate additional conversion of chemical energy to mechanical energy via anaerobic processes. So this light gray area here. And if if someone wanted to run even faster, 26 kilometers per hour, obviously it would take more anaerobic conversion of chemical energy to mechanical energy to be able to run at that speed, because the rate of transforming chemical energy to mechanical energy aerobically was limited in this hypothesis to 4 liters per minute. Okay, and the more anaerobic conversion of chemical energy to mechanical energy that would occur would mean, again, this is the hypothesis, that a greater amount of byproducts of anaerobic metabolism would happen, and that would be lactic acid. And that lactic acid was a result of causing exhaustion and fatigue, and ultimately exhaustion. All right, oh, and here's VO2 in mLs per kg per minute. They wrote it just a little different order, but actually our algebra, it doesn't matter which order that happens at. All right, so so this was the original model of VO2 max. There was this universal maximum rate that would happen. So later on, Taylor and colleagues did the study again, and they took some things away from this study that were then adopted by exercise physiology in general. So here we have rate of oxygen consumption on the y-axis in liters per minute. And on the x-axis is intensity of the graded exercise test. So in essence, it's speed. Now they did also manipulate grade. All right, so elevation, how steep of a hill somebody was running up. But here's speed right here. Right here. So the intensity of the exercise is increasing over time. So the same type of model as what Hill used, except Hill manipulated just speed. And in the open circles represents VO2. And the way that Taylor and colleagues interpreted this is that VO2 increased linearly versus non-linearly from the Hill model, and then eventually reached a plateau. And that what they hypothesized is that this plateau represented the maximum rate that a person could use to convert chemical energy to mechanical energy, right? And what they hypothesized was that this was relative to each person. And it was not necessarily 4 liters per minute, but it was relative to each individual. And so if, in this case, this person wanted to exercise at a higher intensity, they needed more anaerobic conversion of chemical energy to mechanical energy. The byproduct of that, again, is lactate, which then goes into the blood and is detected via a finger prick and measured using some instruments to determine blood lactate levels. And these solid black circles represent the amount of blood lactate in the system. This is a result of anaerobic metabolism of glucose. Here's blood lactate on this axis right here, just so you can see the numbers that correspond with these data points. And as intensity of exercise increases, the amount of blood lactate increases, which means the amount of anaerobic conversion of chemical energy to mechanical energy is increasing. And it would increase, at a faster rate as the intensity goes up. So sort of like what the Hill model hypothesized, is that when greater levels of intensity were done by the person, there's a limiting VO2, and therefore the conversion of chemical energy to mechanical energy would have to happen anaerobically without oxygen, and the byproduct of that being lactate, which then goes into the blood. And that's an important point because we're going to talk about that further. It goes into the blood and detected via finger prick. So this is indicating a greater level of anaerobic conversion of chemical energy to mechanical energy. So this is the history, and this VO2 max plateau was readily accepted, and it's been challenged a bit more now, and I'm going to talk about that. And that's one of the things I really like about Dr. Noakes, Tim Noakes, is his ability to challenge ideas that have been readily accepted. All right, so we're going to talk about this in more detail in just a bit here. So why do people stop exercising? And this is important, is that when you do a graded exercise test, you do try to get the person to the point where they are exhausted and they can't run any further. That's a good graded exercise test. Far too often, people do stop well before they feel they can take that last step. That's okay. We can still look at the data and figure some things out based upon what we're trying to measure and determine. But it really is an interesting question as to why people do stop. Whether or not there's a plateau, that's different. People are exhausted at the end of a graded exercise test, and they may give the sensation that they can't continue to exercise, but rarely do people actually fall off the back of the treadmill, although I have had that happen once. And so we do need to dive into a broader sense of kinesiology and exercise science to really try to understand why people stop exercising, even though they could probably still take a few more steps. Okay, so keep this in mind as we go along. So what Noakes does in this chapter is he really introduces some models. And these models are a way to explain physiological events as well as performance events. And one model that had continued to come back to throughout the textbook is called the cardiovascular anaerobic model. What this model stipulates is that high intensity exercise is limited by the development of anaerobic conditions to active muscles, right? Sometimes Noakes will refer to this as the classic model of exercise physiology, but this is a general statement that corresponds with Hill and Taylor's work, that exhaustion at the end of a graded exercise test is because anaerobic conditions were present in the muscle and ultimately leading to fatigue and therefore exhaustion. This hypothesis also states, this model also includes this information: the heart cannot increase its output of oxygenated blood to the muscles. That's in essence what this statement means in terms of high intensity being limited by anaerobic conditions. Oxygen delivery to the muscles plateaus, forcing the muscles to rely on anaerobic metabolism for energy supply. So these are situations that have to exist in order for the cardiovascular anaerobic model to be accurate, meaning that high intensity exercise is limited by the development of anaerobic conditions. Those anaerobic conditions exist because the heart cannot increase its output, its cardiac output, to deliver oxygenated blood to the muscles. And because of that, the muscles cannot convert chemical energy to mechanical energy at a faster rate, and therefore have to rely on anaerobic metabolism for energy supply. Okay, so that's the cardiovascular anaerobic model, and you're going to want to be familiar with this because he continues to refer back to it in several other chapters. So the question does come back to, does a plateau of VO2 occur during a graded exercise test? Now, as sort of what Taylor, if you look at the figure by Taylor and colleagues, that plateau, does VO2 level off near the end of a graded exercise test? Well, Noakes actually went back, and others authors have done this as well, went back and looked at data that he had and looked for evidence of a plateau of VO2. And from those data, only about a third of the subjects actually had a plateau of VO2. That means that VO2 would have been increasing with exercise intensity along with the increase in exercise intensity, sort of redundant, and the person still chose to stop the graded exercise test. And the plateau is seldom identified in children, as per Rowland and colleagues. The absence of a plateau does not imply that exercise can continue indefinitely. And this is the point I was making before. Exhaustion is real. People do stop, and they are they cannot continue. The lack of plateau, however, means that sufficient oxygen is still being delivered to muscles. Okay, that's important. The lack of plateau means that sufficient oxygen is still being delivered to muscles. There's no limit to VO2 that explains the stopping at the end of a graded exercise test. All right, so let's keep looking at this. If a plateau does exist, that is, if Taylor is correct, or even Hill, that means that inadequate oxygenated blood flow is being delivered to the muscles. All right, that seems reasonable. Remember, this has been something that we've held on for some time, we being exercise scientists. That means that the heart has to be fatiguing before the skeletal muscles, because the heart is therefore limited in delivering the oxygenated blood to the muscles. That's the cardiac output. Ischemic means low blood flow, or low oxygenated blood flow to a muscle. And in a heart attack, we have myocardia, ischemia. Myocardial muscle, heart muscle, is not getting enough oxygen. And typically that's not a good thing. Healthy runners do not terminate graded exercise tests due to chest pain. You don't get that cramp in the heart and say, oh, my heart's hurting, I'm going to stop the graded exercise test. Not in healthy runners. In cardiac rehab, when we would stress test people who with suspected heart problems, we actually did want to elicit symptoms that they were experiencing. And then we could make measurements, whether that be EKG or maybe an echocardiograph, to determine what may be going on. And then the doctor would use that information to determine the course of action. But those are people with cardiovascular disease that they would say, oh, I'm having chest pain. We'd quickly make measurements, stop the exercise, and then go from there. The heart fatigues before skeletal muscles, but there must be, so what Noakes starts to get to is this idea that there must be some protective mechanism to avoid the heart from fatiguing, right? It would make no sense to have the system be able to override the exercise intensity such that the heart would be in risk of damage. meaning the capacity of the heart limits VO2 max. Okay, so this is the argument that he's starting to present in this chapter, is that the blood flow to the heart may actually be a limiting factor to VO2 max, or VO2. All right, so let's look at this a little bit more. And he has this cartoon, this illustration indicating that inadequate blood flow to the heart muscle and what happens, as predicted by the Hill model. So we have maximum limiting cardiac output as the maximum rate of exercise is reached, 13 kilometers per hour from the Hill model. That limits blood flow to the exercising heart, exercising muscle and the heart. Myocardial ischemia causes heart failure. And clearly that doesn't happen. That limited oxygenated blood to the muscles limits or causes anaerobic metabolism of fuel, carbohydrate to yield ATP, stimulating muscle lactic acid production. That lactic acid, in quotes, poisons the muscle, causing peripheral fatigue or causing fatigue at the muscle level. Okay, so this is a cardiovascular anaerobic model. So now, and in this model, fatigue exhaustion is a result of inadequate oxygen being delivered to the muscles. And that's because the heart has reached its capacity. And in one sense, that makes sense, but we're going to talk about it a little bit more in just a second here. So what Noakes introduces is a new model. And this is what one thing that he's very well known for. So you're going to want to be familiar with this phrase, central governor model. He also refers to it as an integrated neuromuscular recruitment model. Either way is fine, but word on the street, central governor model is really the important model that Noakes introduces. What he stipulates is that the heart is at the greatest risk of developing oxygen deficiency during exercise. Okay, you don't want heart muscle to be deficient of oxygen. Therefore, what he hypothesizes is a governor, in quotes, monitors the state of oxygenation of the heart, and maybe other organs such as the brain and maybe even the diaphragm, which is related to breathing. But a governor is something that limits something. School buses would often have a governor on the gas pedal, meaning that the school bus could only go so fast. And so once a certain speed was reached, the governor would kick in and say, okay, no matter how much you press on this gas pedal, we're only going to allow the bus to travel so fast. The same thing, there may be a governor monitoring oxygenated levels of blood to the heart, and that may be detected by the brain. When oxygenated levels approach safe limits, the brain is informed and muscle recruitment is altered. The result of that recruitment of muscle is fatigue, exhaustion, maybe even pain. Individual exercise capacity may be a result of coronary blood flow, heart skeletal muscle efficiency, contractility, and/or elasticity. And I'll explain that a little bit more. So now Noakes is saying that the brain is involved with determining the end of a graded exercise test. And what he has hypothesized is that the heart may be reaching unsafe levels of oxygenated blood. The brain is notified, and then the brain starts to shut down what the muscles can do. That shutting down of what the muscles can do would be something we would pick up as a measure of fatigue, the inability of muscles to continue to generate force with the increase in intensity. And that fatigue would lead to exhaustion, where the brain would say, okay, time to stop exercising because we're reaching dangerous levels. Here's his cartoon of that, figure 2.6. We can start anywhere here, but I'll start up here. Sensory impulse from the brain of the impending oxygen deficiency. The impending oxygen deficiency goes to the brain. Immediate reduction in muscle mass that can be recruited by the brain. So muscles are started to be told to shut down. Reduced muscle activity reduces the work demand on the heart, preventing heart and brain damage. And that's because the governor could be protecting the heart or maybe the brain, and that's what this part here says: inadequate development of oxygen supply to the heart or the brain. As a hypothesis, a statement we believe to be true based upon what we know. So Noakes now gets away from the cardiovascular anaerobic model, and that he introduces this idea that the brain is involved with causing what we see as fatigue or exhaustion. All right, so quick reminder on coronary circulation: cardiac muscle has limited anaerobic ability. Limited anaerobic ability. Cardiac muscle receives oxygenated blood via the coronary arteries. This is the first oxygenated blood really goes to the heart. So the heart gets first crack at any oxygenated blood. Deoxygenated blood is returned via coronary veins. About 70–80% of oxygen is extracted from the blood, 25% in other muscles. So the heart is very effective at extracting oxygen from the blood. Ischemia is inadequate blood flow, as I mentioned, and it can cause angina pectoris, which is chest pain. And we see that a lot in cardiac rehab, and we try to watch for that, because if someone complains of some pain in their chest or maybe some pain radiating down the arm, we immediately lower the exercise intensity to reduce the demand on the heart to pump oxygen blood out to muscles. Cardiac output, you should know this, is the product of heart rate and stroke volume being the amount of blood extracted from the left ventricle with each beat. The amount of blood pumped out of the heart with each beat. That's our stroke volume. All right. So central governor model, VO2 max is a result of maximum pumping capacity of the heart that determines the peak rate that oxygenated blood can be delivered to the muscle. The governor is activated to prevent anaerobic conditions in the cardiac muscle. Anaerobic conditions, lack of oxygen, ischemia. Remember, people are not stopping a graded exercise test because they're complaining of chest pain, healthy individuals. The brain alters muscle recruitment, and that ultimately is explained in fatigue and exhaustion. And later on, we'll talk about this in terms of performance of a 5K, a 10K, or marathon. The VO2 max is also a result of the ability of muscles to generate effective force efficiently. Okay, what's meant by this? Well, all of our muscles have elastic tissue. The elastic properties of each individual person's muscles may help explain VO2 max. Elastic energy does not cost VO2. You stretch a rubber band, you release it, that releasing pulls on the ends of the rubber band. And that does not happen because of any metabolic cost. But same thing in the human body, we have elastic tissue that we can take advantage of, that does not require oxygen to allow a elastic tissue, tendon, to recoil. The level of contractility, and this is important, is that Noakes raises the issue that different people and different muscles may have different levels of contractility. That is, some people their muscles just may be able to contract better than others. And of course, muscles may be more fatigue resistant in one person or another. So he introduces this other model. So now we have cardiovascular anaerobic model, we have the central governor model, and now he stipulates this model, the muscle power model. What this model explains is that an individual's ability to generate force may be because their muscles are simply better at contracting. So muscle contractility, the amount of force that can be generated by a muscle, is not the same in all humans. That could be a connective tissue issue, for example, titin, tendons, but muscle contractility, the ability of each of us for our muscles to generate force, is going to be different. Athletes of differing abilities may differ in the contractility performance of individual muscle fibers, regardless of the type, whether it's type 1 or type 2. but the differences in performance may simply be explained by how well someone's muscles contract. And I'll throw in coordination here as well. Think back to the previous presentation and looking at VO2 max data and different marathon performances, and very different marathon performances, but yet similar VO2 max, or vice versa, similar VO2 max, but similar marathon performances, but very different VO2 maxes. That might be explained by how well individuals contract their muscles and coordinate their muscles. So what does VO2 max mean? Well, it's important to recognize it is not known what causes people to stop exercising during their graded exercise test. Is it a physiological endpoint? Is it a psychological endpoint? Right? This is important because later on we'll talk about fatigue, and fatigue may actually not be a physiological parameter concept. It may be psychological, it may be a perception of how much more we feel we can do. This gets more into the central governor model in terms of predicting endurance performance. That if we don't feel we can continue to exercise, that we may actually start shutting things down and stop exercising. A specific VO2 max does not predict running performance. So that goes back to the previous presentation, the previous part of this chapter. VO2 max is by itself is a poor predictor of performance. This is just to emphasize that point, sort of going along with what was presented in previous presentation, part 1A, is that we have similar VO2 maxes for all these folks up here, each symbol being a different person, but yet here's a wide range of VO2, sorry, I did this backwards. Here's a performance that this person stopped at, or here it is, at about 9 minutes. This person with the same VO2 went all the way to about 13 minutes. So wide range of performances for the same VO2 max. Or if we look at this way, for the same performance in graded exercise test, we have a wide range of VO2 max. So up over 60, and then down here, down in the 50s. Just to emphasize the plateau phenomena, I'm showing these data. I showed these before in part 1A. VO2, time of a graded exercise test, heart rate, VO2 in the red, work rate of the bike in the light blue. And we'd have to just sit back and say, wait, does this represent a plateau? Or is this decrease and then this spike here, is that not a plateau? We really don't know what would have happened if we went to 360 watts. Would VO2 continue to increase throughout that period, or is that evidence of a plateau? Okay, so this is a little confusing, but this is just sort of hammering home this observation of how we can have different performances but the same VO2 max, or we can have different VO2 maxes for the same performance. So for example, Noakes goes through this. You could have a high VO2 max, but you could have a low performance. That means you would have low work rates combined with inefficient hearts and muscles. So maybe you can have a VO2 max of 60 mLs per kg per minute, but maybe you can only run a 5K in 24 minutes, which is not that phenomenal at all. Well, for mere mortals, that's good, but in terms of elite performances, that's not anywhere close to being competitive. That would mean that you're very efficient in terms of a runner, and you're very efficient in terms of transforming energy from chemical state to the mechanical state. Likewise, you could have a low VO2 max, but a high work rate. You could have a great performance, but maybe have a low VO2 max. Maybe your VO2 max is in, the low 50s, but you can run 5K in 18 minutes. That's pretty good. That can still be competitive at an age group level. That would mean that you could have high work rates, good performance, combined with efficient hearts and efficient muscles. That would produce less heat, which we'll get more into in chapter 4 in thermal regulation. That means that the person is able to generate the right amount of force at the right amount of time. That speaks to coordination, as well as even just how each individual muscle um, generates force. All right. So this slide really explains how you can have similar performances but different VO2 maxes, or you could have similar VO2 maxes and different performances. And it has to do with how efficient the heart and muscles are at generating force. All right. So summary of part 1B, VO2 max, plateau or not? It's an interesting question, but really I'm interested, and in this class, we'll probably talk more about why people stop exercising as opposed to whether or not there is a plateau. And going back to part 1A, that's typically why you'll see in literature, people will use VO2 peak as opposed to max, because we really don't know if we're measuring the maximum rate of oxygen consumed. The explanation of VO2 max, you should be familiar with these three models: the cardiovascular anaerobic model, the central governor model, and the biomechanical model. VO2 max does represent the maximum rate of oxygen consumed in terms of the concept. And if we did really want to dial into predicting performance, we probably would need to look at the workload achieved in the graded exercise test at the last stage. And that may actually be good in predicting performance. We'll talk more about that in subsequent chapters. Right, so often you read things like velocity at VO2 max, and that may be a good indicator of performance. Okay, that's it for this part. Thank you.